Yeah? What do you think that means? Probability or chance is the likelihood that something will happen. What do you think that means?
How you expect something to happen?
So what do you think probability means? They say it's chance or the likelihood that something will happen. Explain it in your own words. What do you think it means?
It means anything can happen.
Okay. Saladala Ludo.
Yeah.
You play Ludo. Okay. What's the goal? How charmer dice? What's your goal? What's your goal?
To win.
To win, right? But is it guaranteed that every time you throw the dice or roll the dice, you will get a double six, for example? It's not guaranteed. So think about that, then read that thing again. And tell me what you think about probability. Think about that. Think about probability in the context of Ludo. It's a game that you know. It's popular among the show. I've played it as well. So probability is the likelihood. So likelihood means something you can do. It's not guaranteed, but it could happen. Okay? So you touch a little bit on that when I tell you. So that's what probability is. So I want you to read that line again, but think about it in terms of the game of Ludo. Alright?
Probability or chance is the measurement of the likelihood that an outcome will happen.
Okay. So now, before you start moving your piece in Ludo, you have to score what on your dice? What does your dice have to do?
6.
You have to have a 6, ne? You have to have 2 6s, or at least 1 6.
1 6.
1 6. Okay. So if you have a cube and it has 6 sides, then you have each side has a chance of 1 out of 6 to happen. That's what probability is. So the chance of each side happening is about 16.7%. Okay? So that's the likelihood or the measurement of the likelihood that it would happen. Alright? But we'll get to that discussion as we go forward. So read this part here.
For example, the probability that it will rain tomorrow can be expressed as 80% chance of rain, 0.8 chance of rain, or 8/10 chance of rain.
Okay.
These all mean the same thing as 0.8 is equals to 80% is equals to 8/10.
So 0.8 equals 8/10 equals 80%, e.g. So let's say likelihood of rain, ne? So if they say the likelihood of it raining is 80%, ne? Then on your weather channel or weather forecast, the probability of it happening that it would rain is quite high, right? So probability, long and short, is measured between 0 and 1, or 0% and 100%. Ne? 100% means absolutely whatever is going to happen, ne? Will happen no matter what will happen. Ne? 0% means no chance of it happening. Ne? Yeah. So I like that we're doing probability first, because now you will get to understand common fractions from an application in real life. And I hope that it will also help you understand fractions going forward. But let's start from the back where fractions are applied, because I noticed that you don't really grasp fractions when you're just taught them. So let's rather do it with something that we can work with. So probability is measured from 0 to 100%. 100% means something will definitely happen. 0% means it will not happen. So if something is 80%, that's almost close to 100%. So the chance of it happening is quite high, right? There's no guarantee that our child dies in Ludo, you'll score a 6. You could score a 1, or you desire a 6, but you could score 1, right? You would desire a 6, but you could score 3. You would desire a 6 and you could score 5. And that's what makes the game fun. But if the cube, the dice or the die had all 6s, then anytime you roll it, it will always be a 6. Anytime you roll it, it will always be a 6. So the probability of scoring a 6 with a die will always be 100%. Ne? Goes back to the definition. Chance. That's probability. Right? It's chance. Okay? Then the next part.
When we know the probability of an event happening, we can use its value to predict the likelihood of a future result.
Okay.
If there is a prediction of 80% chance of rain tomorrow, we can predict it is likely that it will rain tomorrow. This does not mean it will definitely rain, but it will probably will.
Okay. So an 80% chance of it raining does not necessarily mean that pula, but it means if you washing, if you do your laundry and you hang it tomorrow and there's an 80% chance of it raining, you might have to dry your clothes for another day. So you're taking a gamble with whether or not it will rain. And if it looks cloudy and the weather forecast says 80% chance of rain, then what you're saying is, I'll wash my laundry and I'll hang it, but I'm okay with hanging it another day or keeping it in the house and then it comes smelling sour. That's what it means. Ne? Okay. And then probability scale.
The probability scale. Probability can be measured on a scale from 0 to 1 or 0 to 100%.
Okay.
A probability of 0 means that there is no chance of the event happening. For example, the probability of Christmas Day falling is in April. For example, the probability of Christmas Day failing in April is 0.
Okay. Think about that. Ne? Christmas, how often does Christmas come in a year? Once. On which day of the year on which month and on which day of that month does it come? December 25th. Will Christmas come on May 1st? So what's the probability of Christmas falling on May 1st? What's the chance that you'll have Christmas on the 1st of May? 0. So is it starting to make sense how you interpret the probability scale? Okay. So we can't have Christmas in May on 1st May. That's no chance. Ne? Okay, carry on.
A probability of 1 means it is certain the event will happen. The probability of the sun rising in the morning is 1.
Okay, good. 1 over 1, then 100%. Ne? So, will the sun rise tomorrow in the morning? Okay, so what are the odds that it will be tomorrow? What's the chance that it will be tomorrow? It's not that difficult. It's 100% chance, right? Yes. I'm asking a very simple and obvious question because it is what it is, right? And that's all there is to probability, right? But you need to understand this before you can understand tree diagrams. So sun will definitely rise tomorrow in the morning. Ne? Okay, carry on.
The sum of all the possible probabilities will equal 1 if the data records all possible outcomes of the situation and the outcomes do not occur on the same time.
The sum of all the possible probabilities will equal 1 if the data records all possible outcomes of the situation and the outcomes do not occur at the same time. What's the best way to explain that? Okay, we'll get back to that. Yes, expected or theoretical probability. Yeah? So then there's theoretical probability. What does that mean? Read for us there.
When there is no reason why one outcome of the experiment should occur more frequently than another, we say that the outcomes are equally likely. When an unbiased coin is tossed a large number of times, there is no reason why more heads should turn up than tails. Heads or tails should be equally likely to turn up.
Okay. Okay, so let's play a game, ne? Theoretical probability versus relative probability, ne? Probability, ne? Let's play a game. We've got Kopano and we've got Talis, ne? If you had to choose a coin, which is the side of a coin, who's gonna take heads, who's gonna take coin? Tails.
Tails.
We'll take tails. Okay, so tails, and then you take heads, ne? So we're gonna play a game 10 times, ne? So okay, let's start here. Coin has two sides. What's the chance that you will get heads in any coin toss? What's the chance that you will get heads?
1%.
No, that's not 1%.
Out of 100,
Yeah, out of 100. 50, alright?
Oh, 50-50.
50-50. That's why it's fair. So 50% chance means it's a fair chance. That is why when soccer match starts, the team captains or whoever represents the team goes to the center of the pitch with the referee. They do a coin toss, and then it's decided who's gonna score in which direction first. Fair play. Alright? Okay, so if we know that in one coin toss you have 50% chance of head showing at the top and you have 50% chance of tail showing in the top, then it means it's a fair game. So now what happens when we do this 10 times? Let's do that experiment. Ne? So we're gonna do this experiment 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ne? 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so I'm gonna flip the coin once. Ne? Agree your heads, his tails. Okay, so Kopano's the first choice goes to Kopano. Ne? And the second choice, let's see, where does it go to? It also goes to Kopano. Well done. Third toss, tails, goes to Taviso. Well done. First time. Next one. Heads. Okay. Fifth one. Tails maybe. Okay. 6. Heads again. tail. Tail. So you are all equal. Heads. Kopano leads again. The last flip. Heads. Okay. So for Kopano, the probability or the chance of getting heads is 1, 2, 3, 4, 5, 6. Ne? 6 times out of 10 times. Ne? That one is a common fraction. But we can also express it as 0.6 or 60%.
Alright.
Yeah.
It's not common fractions, it's common factors.
Buzz, you said common fraction.
Sorry, it was a mistake. Ish.
Is it common fraction? So one.
Ish.
It's fine. We'll do that. Then for Tabiso, it's 4 times out of 10, or 0.4, or 40%. Right. So in our experiment, 60% of the time, it was heads, and 40% of the time it was tail. Now carry on.
Similarly, when a pair dice is rolled, each of the 6 numbers will be equally likely to turn out.
Okay.
To calculate the theoretical probability of a situation, take the number of outcomes of the desired event and divide it by the total number of possible outcomes.
Okay, that's good. So let's start again with coin toss. Ne? So let's look at coin toss. The book, the description says the chance of something happening equals number of desired outcomes. Ne? So outcome that you wanted when you were doing the coin toss for Kopano was heads and for Tabiso was tails, right? But the number of possible outcomes, how many possible outcomes do we have? If we have a two-sided coin, how many possible outcomes do we have?
10. 10.
No. You're thinking about the game you just played. That's not what we're asking. Possibility on one coin, there's heads, there's tails. How many possible outcomes do we have if we only have heads and tails? 2. So, number of possible. So, again, you say you want to be a rapper. So you gotta be paying attention to word use, vocabulary use. I get it? So if you're not paying attention to what we're saying in class or words that are used in the textbook, lyrical content is just gonna be like these. But anyway, so if we're doing a coin toss like we just did now, either of you wanted heads and either of you wanted tails. One of you wanted heads, one other wanted tails. So what it means is the desired outcome is the desire that you want. I get it? So if it's heads, that's one desired outcome. But the possible outcomes, there's heads and there's tails, so there's 2. So what that means is then for a coin toss, you get 1 desired outcome out of 2 possible outcomes. And this is 0.5, which is 50%. So out of 100%, there's a 50% chance that you will score heads or you will score tails. And anyone who's flipped a coin knows this, at least from internal, without having to be taught it. But now we're studying it. I get? Yeah. Now let's look at rolling a die. Ne? When we roll a die, we have to look at how many possible outcomes there are if you roll a die. How many are there if you're rolling a die?
6.
6, ne? And why is that?
Why?
Yeah, why is that?
Because it has...
Because it has 6 sides.
Because it has 6 sides, yeah. What were you gonna say?
The dots.
The dots, yeah. So 1 dot for each side, right? I'm just gonna connect this. It should be here. This is like another exercise. I don't want to talk about it in class, but okay. So I'll just put that there. Okay, so when you are rolling a die, there's a number of desired outcomes. And okay, you're playing Ludo, you want to start moving your piece around. What's the one outcome you desire?
6.
To have a 6 facing up again. So there's one outcome. Ne? Outcomes. So that's one desired outcome. But how many possible outcomes are there when you're rolling a die?
6.
6. Excellent. Why is it 6 again?
Because it's 6 sides.
6 sides to a die, right? So this becomes 0.166. Okay. So, oh thanks. All right. So that's what that means. Theoretical probability. Ne? Yeah, that's what that means. So theoretical probability, I like that they put it as expected probability. Ne? What do you expect will happen if you flip a coin or you roll a die? That's what you expect when you do that, right? Expected probability. Ne? Yeah, you're able to see. Okay, then continue reading from there. What does it show? Example. Okay, Camilla the florist is making a bouquet. Next to her is a bucket holding 7 yellow irises and 4 lilies. If Camilla reaches into the bucket without looking and takes a flower at random meaning raffle, like, ne? What is the probability that the flower is a lily? Ne? So let's look at that example. Let's study that example properly. Oh yes, it's here. Let's look at that example. So there's 2 types of flowers, ne? So a florist has 2 types of flowers. So a florist has a bucket with 2 types of flowers. The first type of flower is iris. The second type of flower is lily, ne? And that bucket, so these are in the bucket, ne? How many flowers in total are in the bucket, according to the example? 11 flowers, ne? 11 flowers in total. And so if it's 11 flowers in total, how many irises do we have in the bucket?
7.
So it's 7 irises, not ICCs. And then how many lilies?
4.
4. Okay. So she now wants to take out a flower. But she wants to take out which flower specifically? Lily. Ne? She now wants to pull out a lily from the bucket. So if there are 11 flowers in total and only 4 lilies, we're going to work out the probability that she'll pull out a lily from the bucket. Right? How are we going to work that out? So the chance is the probability that she'll pull out a lily. So this is how we write it out, right? The probability of event A, right? So we're going to look at the definition of theoretical probability or expected probability, which is number of desired outcomes, and we're going to divide it by the number of possible outcomes. Okay, so this florist, which flower does she want to pull out?
Lily.
Lily. Okay, and how many outcomes are there for the lily? If you were to think about it, what would you say that would be? We can talk about it. I mean, we don't have to put ourselves under pressure. Let's just talk about it. There are 11 flowers in the bucket. 4 of them are lilies, 7 are irises. Out of 11 flowers in total, she wants to pull out a lily. So which one does she desire? It's lily. So how many chances or how many outcomes would she have an access to?
Plus, I think 4.
4. Okay. Why do you think that's 4?
Because there's 4 flowers.
4 lilies.
Yeah, 4.
Yes. So 4 lilies are the outcome that you will have if she were to pull out a lily. So that's 4. But how many? So what's the total number then of possible outcomes?
40%.
No. We're just looking at this definition first. Number of desired outcomes, and then we are also looking at number of possible outcomes. So we've just established that she would desire to take out a lily, meaning there's 4 desired outcomes to get a lily from reaching into the bucket and pulling out a flower. But now, if there are 11 flowers in total in the bucket, what's the total possible outcome, the number of possible outcomes?
11.
It's 11. Okay, that's good. Why would you say it's 11?
Because the flowers are 11 in total.
In the bucket, ne? Yeah, so the possible outcomes are 11, but the desired outcomes are 4. So then the probability of drawing a lily from the bucket is 4 out of 11. And if you divide that, that would be it goes 0 into 4, 11, 22, 3, it leaves 9, and into 90 it would go maybe 80 something. So 0.38 something. Let's quickly check. Calculator. If you say 4 divided by 11. Oh, 36. Now one. So about 36.4% chance that she would draw a lily. Okay. So is it starting to open up how we can think about probability? Okay. let's look at this example. Read it out for us. Or rather, activity. Yeah.
Susanna is decorating cutlery with different colored beads for the school market day.
Okay.
She has a jar that contains 200 beads. 50 of the beads are blue. What is the probability that a bead selected at random is blue?
Okay. So there are 200 beads. Oh yes. So there are 200 beads, and 50 of those beads are blue. You don't know what other colors the rest of the beads are. So we need to find the probability that a blue bead is drawn. Ne? So what's the desired outcome? How the number of desired outcomes in this case?
50.
50. Okay. Why would you say that is?
Why?
Yes.
Because there's 50 blue beads.
Okay, wonderful. That's perfect. Thanks for sharing. Ne? Number of desired outcomes. Why is my spelling so terrible today? Number of possible outcomes. So that would mean 50. But now what's the total number of possible outcomes?
200.
200, yeah? So that means 5 out of 20 goes once, goes 4, 1 over 4, which is so the possibility is there, but it's not that high. Alright? The probability, the chance is there, but it's not that high. It's only like 25%. So at any given time, she could pull out a different color but blue. So if you're in the situation you have to make an item with beads and you have to choose blue beads first or select blue beads, what would you do? Would you continue guessing and hoping that it's a blue bead, or would you say, I've got 200, let me put the 50 blue aside, let me put whatever color there? And
Yeah.
you'd probably do that, and that would make your work easier, right?
Yeah.
So I wonder how it helps to think about some of these things mathematically, because then you're like, if the probability of me getting blue, let me just rather, be organized, and then, so it helps with decision making. Yeah. And then the next one.
When a fair dice is rolled, what is the probability that it lands on A, an odd number, B, the number 4, C, a 0?
Okay, so a die is rolled, ne? Die rolling. By the way, we have one die. This is singular form, ne? This is English grammar. And 2 dice, plural, ne? All right. So die rolling activity. What does it say?
When a fair dice is rolled, what is the probability that it lands on A, an odd number?
Odd number. Okay. What's an odd number?
1.
Okay. What else is an odd number?
4.
4. No.
3.
4 is not 3. Okay. Okay. What other odd numbers can you think of?
5.
5. Okay. Are you starting to see the pattern?
7.
7. Okay.
9.
9.
11.
Yes, those are odd numbers. You can divide it, but it will leave a remainder. So if you divide 5 by 2, you get 2.5. If you divide 7 by 2, you get 3.5. But an even number, if you divide it by 2 or an even number, you'll still get a square number, so to speak. So you won't get a decimal or a fraction or whatever. Yeah. All right, so odd number. Now let's think about this. Okay. So the probability of odd number when rolling a die. What's the number of okay, we'll start with number of desired outcomes. I guess sometimes you have to take your piece home in Ludo. Sometimes you need to count 1, 2, 3, and then you're in, right? You're in safe. Sometimes you need to do 1, 2, 3, and then 4, you're safe. So if you do 1, 2, 3, 4, you're safe, that's even number. But if you do 1, 2, 3, you're safe. That one. So let's say we've got a piece J2. One needs 1, 2, 3, and the other needs 1, 2, 3, 4, 5, and then it's safe. So the other one needs 1, the other one needs 3, the other one needs 5, right? Yeah, the other one needs 1, the other one needs 3, the other one needs 5. Those are odd numbers on a die, right? Now we want to find the probability of a die landing on an odd number. There's 3 odd numbers on a die. So what is the total number of desired outcomes?
5.
It's not 5. Think about it. Remember, we want to, every time we roll the die, we should have an odd number. That's our desire. And our odd numbers, when we have a die, between 1 and 6, how many odd numbers do we have? From 1 to 6, how many odd numbers have we got?
3.
We've got 3, it's
1, 3, and 5.
and 5. So we've got 3 odd numbers. Those are our desired outcomes. So how many desired outcomes do we have? 3. Awesome. And how many possible outcomes do we have?
6.
6. Okay, so do you see what that gives us? 3 out of 6. 3 goes there once, it goes there twice, and it's a half. 0.5, 50%. You get it now, Papa? Alright. Then the other one says what?
The number 4.
The number 4. Okay. Number 4. So what's the probability of landing a 4? How many desired outcomes do we have?
3.
How many 4s are on a die?
Oh, wow.
So we desire 4, and there's only one time that 4 would happen. But how many possible outcomes do we have?
6.
6. Alright, so again, that's the probability of having the number 4. And by the way, this probability is also the same for the number 1, the number 2, the number 3, the number 5, and the number 6. Because each one of them has 1 out of 6 probability of showing up when you roll the die. Yeah. Then the third one asks for what?
Is 0.
0. Okay, now let's talk about this. What's the probability of landing a 0 when you roll a die? How many desired outcomes do we have on a die?
6.
Desired outcomes on a die that will give us 0. How many of those do we have?
3.
1.
Think about it. So I roll a die, say, and then we get 0. So how many, like, if that's the desired outcome, actually, if that is the desired outcome, it's 1. Yes, you said that, ne? You said that, okay. But is it possible? It's not possible. So we get 1 divided by 0, and it's like, it's undefined. If you take a calculator and you divide anything by 0, what does it give you as an answer?
0.
What does it say? It says error or syntax or whatever. Yeah? Yeah, so it just tells you that, hey, this thing is not possible, at least in the real number system or in anything that's real. That one. So yeah. Calculator.
Probability of being born on a Friday.
Okay, now it's getting wild. Yes, like being born on a Friday. Okay. I'm not gonna say that the thing we're gonna do is correct, but let's stick with the definition, right? We'll call it being born on a Friday. So the probability of being born on a Friday. Okay. Number of desired outcomes divided by number of possible outcomes. Okay. So the desire is to be born on Friday. How many days of a week do we have? 7. Okay.
Friday is the 5th.
Friday
It's the
is the 5th day of the week. It could be the 6th depending on when you start your week. But it's fine. So, but it's one of the days in the week, yeah? It's one of the days in a 7-day long week. Okay. So, that would be one day. This is my guess. And the possible outcomes would be how many? 7. Okay, so there's a 1 out of 7 chance that a person could be born on a Friday. Or is it so? You can check another source. You can check another source. Probability of being born on a Friday. So it is 1 in 7. All right. So, but you get the idea now almost for probability, ne? God, she has to draw. Okay, so you can do those exercises for yourself. Then I guess it's also the same. Probability of an event not happening. Okay. Oh, okay, cool. I think that's an important thing. So there's something called probability of something not happening. An event not happening. Ne? So, okay, read for us that part there. This paragraph. The sum of
all the possible outcomes in an event equals 1. So if the probability of an event is P, the probability of an event is not happening is 1 minus P.
Okay, so let's say event A has a probability of event A happening, yeah? And then we say so it has a probability of A happening, but event A not happening, then it has 1 minus the probability of A. Ne? So the sum of all probabilities always equals 1. Ne? The sum of all possible outcomes in an event equals 1. So if an event would not happen, if we have an event having a probability of A happening, then it has the probability of it not happening is 1 minus the probability of that event. So we can look at an example. Read this part. And Haneli.
Haneli takes a scarf from a bargain bin at random.
Okay.
The probability that it is a pattern scarf is 0.3.
Okay.
What is the probability that the scarf is not patterned?
Oh, okay. So you're gonna buy so just say you go shop, right? And well, let's make it interesting. So leisure apple munch.
Yeah.
Alright, cool. So there's 12 of those in a pack, right? It's 12 of those in a pack. Let's say you put them in the freezer 4 hours ago, not overnight, maybe 4 hours ago. So some would be frozen and some would not be frozen, right? Let's say the probability of let's say in 4 hours at least one of them will be frozen. Ne? So then that would mean, so we've got 12 lollies, 12 ice pops, ne? After 4 hours of putting in the freezer, maybe one of them is frozen. So the probability that you will get a frozen ice pop would be, or apple munch, frozen, would be, the desired outcome would be 1, but the possible outcomes would be 12. But then, what is the probability that you will get an apple munch that is not frozen? That's what we're trying to calculate. So that would be 1 minus the probability of an apple munch being frozen, which is 1 minus 1 over 12, which would be 12 over 12 minus 1 over 12, which is 11 over 12. So think about it like this. I get it, you've kept them in the freezer. Not all of them are going to be frozen, but maybe let's say one is like that cold and then it freezes quick. So that means out of 12 units, one will be frozen. Right? So the probability of getting a frozen one is 1, which is the desired outcome, out of 12, which is the possible outcomes. There are 12 apple munches in a pack. Right? So what is the probability that you will pick an apple munch at random, but when you pick an apple munch at random, it is not frozen? It's not 1 over 12, because we know that 1 over 12 is for picking one that is frozen. Does it make sense? Yeah. So how you work that out mathematically or in terms of numbers, then it will be 1 minus the probability of getting a frozen apple munch. Now when you do the math, 1 is the same as 12 divided by 12, because 12 divides into each other once. And you understand this step?
Yeah.
Ne? Understand the step, okay. So then it becomes 12 divided by 12 minus 1 over 12, which is 11 over 12. So there's a higher chance of getting a non-frozen apple munch than there is of getting a frozen apple munch. Alright? So that's what this example is about. Alright? Let's look at another activity. It says what? A coin is taken at random from a bag of coins. Ne? The probability that it is a 1 rand coin is 0.25. So the probability of 1 rand coin equals 0.25. Ne? Is 0.25. Then what does the question say going forward?
What is the probability that the coin is not a 1 rand coin?
Okay, so the probability that the coin is not a 1 rand coin would be 1 minus the probability of a 1 rand coin, because the sum of all possible outcomes equals 1. So it's going to be 1 minus 0.25, which is 0.75. So let's say you're busy selling a cash business then. You're selling sweets and apple munch and cool time, airtime. People are buying with cash, right? And you have a pouch here in front of you, strapped it onto your body so that people don't take it from you. And there's a lot of coins in it so that you can give people change, right? You're a street merchant or a hustler or a business person in the street shop. Now, you've got coins in there, and there's a probability that you would draw a 1 rand coin. Let's say you're selling me apple munch for 2 rand. I buy 2 apple munches with a 5 rand coin, and you have to give me 1 rand change. You want to give me 1 rand change because maybe you've got few 5 bobs and you don't want to give 50 cents away because that might mess up your cash flow, and you can't give me 2 rand because that's more than the change I deserve, right? So you sticking your hand in the pouch, you want to pull out a 1 rand, but the probability of pulling out 1 rand is 0.25, right? 25% chance. The chance is there, but it's small, right? What is the probability that I'll pull another coin? So in other words, what's the probability that I will not pull out 1 rand coin, or you will not pull out 1 rand coin when giving me change? That's what we're calculating. So what that means is, I have to take 1, which is the total sum of all possible outcomes, and I subtract the probability of pulling out 1 rand. So if I take 1 and I subtract 0.25, I get 0.75. So what does this tell us? It tells us that if I stick my hand in the pouch, or if you stick your hand in the pouch at random to give a customer a change of 1 rand, there's a higher chance that the coin will not be a 1 rand coin. So what's the easiest thing to do? Probably to take out more coins, and then you see. so that's what this is. That's what this exercise is. Yeah, and I believe all of these examples are that. Right, then we're gonna quickly do this for the next 10 minutes before we stop and switch over to common factors. Yeah, all right, cool. So 2-way tables and tree diagrams. All right, 2-way tables and tree diagrams. So another thing about these subjects that we do, must remember they're written in English. So even though it's not our mother's tongue, you just have to read the English as best as you understand. And where you don't, refer to maybe a dictionary or ask what the word means if you're not sure. But more times than none, you are likely, it's probable, there is a probability that you will understand the math if you read through the language. That's why I always encourage reading, guys. It's not to make you feel some type of way about how you read, or I encourage the reading so that you understand the language, so that when you understand the language, you can do the math, because the math is carried in the language. Yeah. So, and I'm saying this intentionally, because 2-way tables and tree diagrams, once we start to do them, you'll understand what that concept means. Yeah. So read for us there.
To find all the possible outcomes when two events are combined, list the outcomes systematically. Use a two-way table or draw a tree diagram to show the probability of a certain outcome happening.
Okay.
Two-way tables and tree diagrams are useful visual ways of representing probability so that it is easy to understand and to calculate.
Okay, so this thing of tree diagram, it tells you it's a tree. How does a tree grow? You have the ground there, you plant a seed, and after some time it germinates, it starts forming roots. So as the roots shoot into the ground, it starts growing out. After some time, these become thicker or larger, right? And your tree would have, let's say, a taproot and some adventitious roots, but it will also take form outside and it will have branches, right? Isn't it? Isn't it? So trees would branch and every branch would start branching, etc., right? Branch, 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 branch. And then sometimes you have to cut it because it will like a kigarani, which and guava and mango. And then they're like, no, we don't eat guava. Maybe they do, but they're like, why do you have to have a guava tree? So, but the point of tree diagram will show you how we can map different possible outcomes from separate events. All right, so let's do a coin and a dice that are thrown. So for some reason there is a game, and that game features rolling a die and flipping a coin. So we're gonna do that. So coin toss plus rolling a die. Okay, cool. So list all the possible outcomes and find the probability of the coin showing heads and the die showing a 6. So we have to list all the possibilities of the coin toss and the rolling of the die so that we would land a 6 and we would also land heads. That's what we have to do in this example. And what is the solution? So we've got heads and a 1, right? Then we've got tails and a 1. Then we've got heads and a 2, heads and a tails and a 2. Then we've got kanjal, right? Heads 3, tail 3, heads 4, tail 4, heads 5 and tails 5, as well as heads and a 6 and tails and a 6, right? So there are 12 possible outcomes. In only one of those outcomes does the coin show heads and the die show a 6. Therefore, the probability of getting a heads and a 6 equals 1 out of 12. Alright, so what does that mean? How many possible outcomes do we have here? Let's start there. 12, ne? So possible outcomes 12 and desired outcomes 100%. Yes, that is very correct. Therefore, probability of heads and a 6 would be 1 out of 12. Alright. Now we can show this by using a two-way table or a tree diagram. So how do we use a two-way table? Read that first thing.
A two-way table can only be used when two events are combined. Place one event in the first row and the other event in the first column. In the coin and dice experiment, the throw of the coin only has two possible outcomes, heads or tails.
Mm-hmm.
The throw of the dice has six possible outcomes. 1, 2,
-1.
minus.
No. It's just like,
Oh, it's a.
yeah, it's a.
So.
But it's fine. It shows you engage in the content, so it's fine. But yeah. So it's 1, 2, 3, 4, 5, or 6. Yes. Okay. If you
multiply the possible outcomes of the first event by the number of possible outcomes in the second event, you get the total number of possible outcomes. In this case, 12.
Okay. So think about it like this, ne? Two-way table. The first way is rows. So way 1 is row. And then the second way is column. Ne? Which is that way. Ne? So in our previous example, the coin toss has got heads or tails, right? So we can write rows. Rows is like going across, columns is going vertically. Ne? Right, so we would have heads and tails, right? Now the second event is 1, 2, 3, 4, 5, 6. So you have something like that. Alright. So heads with 1, there's one possibility. Tails with 1 is another possibility. Heads with 2 is one possibility. Tails with 2 is another possibility. Heads with 3 is one possibility. Tails with 3 is another possibility. Heads with 4, another possibility. Tails with 4, another possibility. Same with 5 and same with 6. But now if we are seeking this particular outcome, which is having heads and a 6, we will have 1 out of 12. So that's the two-way table, right? And what does it say at the bottom? Well, that last line there.
If you multiply the possible outcomes of the first event by the number of possible outcomes in the second event, you get the total number of possible outcomes. In this case, 12.
So think about it this way, ne? So this is event 1. Let me use red. Ne? So heads and tail are event 1. And I'll use green for the other one. So 1, 2, 3, 4, 5, and 6 are event 2, right? So all of these going this way are event 2, and all of these going this way are event 1. So if we have 2, so let's look at event 1. How many possible outcomes do we have in event 1? We have heads and tails. How many possible outcomes do we have? 2 heads and tails. And then if we look at 1, 2, 3, 4, 5, 6, that's event 2. How many possible outcomes do we have in event 2? 6. Yeah. Do you get right? 6. Okay. So if we multiply 6 and 2, that gives us the total number of events. So 6 by 2 would be how much?
12.
It would be 12. So that would be the total number of events, which takes us back to, if you go back to the previous slide, it takes us back to that. Possible outcomes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We get it. But the desired outcome was head and 6, which is 1. The total possible outcomes was 12. So that's the two-way diagram. So we've got two events, the number of outcomes of event A and the number of outcomes of event B. Then we multiply the two, that gives us the total possible outcomes. Yeah. When we're just looking at event A, which is heads or tails, we only have two possible outcomes. When we're looking at event B and we're looking at total possible outcomes, it's only 6 outcomes. But when we combine the two and we have event A and event B, then number of outcomes for A multiplied by number of outcomes for B gives us the total for both events at the same time. You get it, né? Okay, so let's do how to use a tree diagram. And then we close this part. Tree diagram. Alright, oh yes, just do 14. That's fine. Alright, thanks. Okay, so read for us there how to use a tree diagram.
A tree diagram can be used when two or more events are combined.
Okay.
There is a split in the tree every time an event takes place.
Okay.
Like the toss of a coin. The number of possible outcomes of each event determines how many branches the tree has.
Okay.
On the left side of the page, list all the outcomes of the first event. List each outcome of the second event next to each outcome of the first event. The number of outcomes on the far right of the diagram shows the number of all possible outcomes.
Okay. So a tree diagram for the coin and dice experiment, né? So we have here where we start, né? So on the left we'll have a coin toss. Let me just draw that a little bit to the bottom of the page. So in our coin toss, that would be event A, né? So this part here would be coin toss, né? And there's a 50% chance and a 50% chance. So in other words, this part of the tree, the first branch, that's for, could be heads and it could be for tails. Remember, the expected chance of a coin toss for either outcome heads or tails is 50% or half. It's 1 out of 2. Né? Then, so we'll say this is for heads and that's for tails. Okay. Then what happens after that part of tails? We get the dice, the rolling of the die. So for heads, with 1 or 2 or 3 or 4 or 5 or 6, we get the same, we get the number of branches that corresponds to the outcomes for rolling the die. So we would have 1, 2, 3, 4, 5, and 6. And we also have 1, 2, 3, 4, 5, and 6. Ne? And that will give us 6, 5, 4, 3, 2, 1. 6, 5, 4, 3, 2, and 1. Alright? So what does it say about possible outcomes? Okay. So possible outcomes, ne? Would be heads and 1, heads and 2, heads and 3, heads and 4, heads and 5, as well as heads and 6. We're still doing the same table, but this time we're looking at it as like a tree. You see? And then here we'll have tails with 1, tails with 2, tails with 3, tails with 4, tails with 5, and tails with 6. You follow? Okay. Then read there at the bottom.
to find the probability of a certain outcome, multiply the probabilities leading to that outcome. In the coin dice experiment, the probability of throwing a head and a 6 is calculated like this. Probability heads and 6 in brackets is equals to 1 over 2 multiplied by 1 over 6 is equals to 1 over 12. Notice that the fractions have been taken from the tree diagram.
Okay. So, right. So remember the possible outcomes for heads and any one of the numbers on the die. It's H1, H2, H3 up to H6. Same with tails. So that means even if you were to calculate the probability of tails and the number 1, you would have the probability of tails would be 1 over 2, and we multiplied by the probability of the number 1, which is 1 over 6. Desired outcome for number 1 in rolling a die is 1. Possible outcomes is 6. Desired outcome for tails in flipping a coin is 1. Possible outcomes is 2. So we take 1 over 2 times 1 over 6. And when we multiply fractions, we usually multiply across. So we'll have 1 times 1 is 1, and 2 times 6 is 12. And that's how we get to the answer. So it's starting to be clearer now. Okay, and then next page. Okay, so 2 coins are thrown. Find the probability of getting 2 heads, a tail, and a head in any order. Let's do that one quick before we finish off probability for now. So, activity. So 2 coins, they're thrown. Find the probability of getting 2 heads and then a head and a tail. So let's start with two-way table. So two-way table. So coin would give us heads and tail. That's event A. And the other one will also give us heads and tail. That's event B. Event A. And going this way would be event B. Right. So we've got heads and heads, we've got heads and tail, and then we've got tail and heads and tail and tail. Right? So possible outcomes is 4. Then the probability of a desired outcome heads and heads would be 1 out of 4 from the two-way diagram, right? And then the other one would be a tail and a head in any order. So it could be a head and a tail. Yeah? So the probability of head and tail would equal so for the first coin it would be 1 over 2 to get a head, and for the other possibility would be 1 over 2 to get a tail. So then we'd end up also with 1 over 4. Is it correct? Head and tail, tail and head. It's actually supposed to be the other way around. There's something I didn't do right here. No. I'm going to ask myself the same question before I give you a final answer. Head and tail. Probability of head and tail would be 1 out of 2. And also the probability of getting head and tail. Let me check something before I continue. two-way diagram, coin toss. All right. Let's look at this one. Quora. What is the diagram for coin tossed twice? Yes, let's look at that one. Quora. Continue reading. Okay. I'm assuming this is a standard for a coin with an equal chance of either getting heads or tails. Yeah, I want to read this one. Okay, science, business, I'll say finance, I'll say marketing, maths. Okay, it's fine. Choose more topics as we continue. One of two answers. Oh yes, more. Maybe not. Let's go for. I just want to see something before I give you a final answer. Let's say we flip two coins. The probability of first coin is a head is that. The second coin is a head is that. In fact, what happens with the first coin has nothing to do with the second coin, and the events are independent. And the same argument, two tails is 1/4. Okay, so heads and tails and tails are 1/4. That's great. The question of one head and one tail is a little more complicated, for there are two ways this event can occur. We would get head and then tail and then tail and then head. We combine the conditional probability, and yes, that's why I'm like, it can't just be that by that, né? Because when you look at it in tree diagram, you will have coin 1/2, 1/2, and then you get heads and tail, alright? And then when you look at it with the second coin, this would also have a 1/2 and a 1/2, and you'd have heads and tail, and also here and there, and you'd have a head and a tail. So what does this tell us? It tells us that it doesn't matter the order of a head or tail and head, but what we do know is the probability of two heads is 1.5. It's half times half, which is 1/4. But since there are two leaves corresponding to one head, each of the probability of 1/4, then the probability of this event is 1/2. So wait, what? probability of 2. Since there are 2 leaves corresponding to 1 head and 1 tail, probability of each being Okay, can I pause here so that we don't eat up Taviso's time? I'm going to study this one a little bit more and then we'll come back to it. Ne? But tree diagrams, long story short, you get event 1, you split it, and then the second event for the you split it according to its outcomes. Yeah. So this is event